All right, so definition. Let's let f be a function defined on a closed bounded interval, ab. Then the Riemann definite integral of f on ab, which is denoted with this symbol. So this is called the integral symbol, and you write from a to b, the integral from a to b of f of x dx. The dx right here is, for now, just telling you that you're integrating with respect to the variable x. We're working with x. We want those variables to be the same. And so this is defined as, let me erase this. It's defined as, okay, it's a limit as n goes to infinity of this guy. This looks like what we just did. It is actually. We're going to factor out this delta x, and then we're going to use the sum symbol. So this sum symbol just means sum. It just means add, starting at 1 to n. So f of x1 star delta x plus f of x2 star delta x. So this is a mathematical notation to try to shorthand that. And you're taking the limit as n goes to infinity of this guy. What's delta x? Same as before. It's b minus a over n. And then xi star is a test point from your little interval. So you're still breaking your x-axis up into little intervals. You're plugging in a test point, and you get this. Okay, now, here's the deal. We really don't want to spend a lot of time working with this definition, so I want to give you the key takeaways here. So here's a series of remarks that are going to help, hopefully. So first remark, in general, your function might dip below the x-axis. And what does that mean for area? What that means is you can't interpret, you can no longer interpret the integral from a to b of some function f of x dx. This might not be just area, okay? When the function goes below the x-axis, then you interpret this as actually negative area. So let me show you how this works. If you have area 1 here, area 2 is the pink, area 3 is the green, and you have the integral from a all the way out to b of f of x dx, then it's the sum of the positive areas. It's area 1 minus area 2 plus area 3. So this definite integral does have everything to do with area, but it might not equal area itself if your function dips below the x-axis. So we still do the rectangles. You're still estimating and taking a limit and doing that, but the answer that you get might not explicitly be area. In this case, it's not going to be the sum of these three areas. Whoops, I want to erase that. It's going to be the positive area, the positive area plus the positive area minus the negative area here. Okay, so next thing is we pointed out on the above definition that this definite integral is a limit, and that limit might not exist. There's actually lots of functions for which it doesn't exist, but as long as your function is continuous, if you're working with a continuous function, then you know that the definite integral exists. So in our new notation, the problem that we worked out just a few minutes ago in the last video, the integral from 0 to 1 of x squared dx, that would equal to a third. And in this problem, it is area. You can interpret this integral as area because x squared stays above the x-axis. So that's the notation now for what we've been doing before. So I thought we would do some examples. I think I need to erase a few things, actually. So let me just quickly erase. I forgot to do this. So I want to work out this problem with you. And let's see if we can do it. So first off, I'm going to graph y equals negative square root of 4 minus x squared. And I'm going to square both sides, and I get y squared equals 4 minus x squared. So y squared plus x squared equals 4. That's a circle centered at the origin of radius 2. But the negative square root, right, is the negative. It's the bottom half. So you're actually looking at this guy right here. And so when you compute the integral from minus 2 to 2 of this function is below the x-axis. It's down here. All right. the negative is a part of this, right? The negative puts you down here. We expect to get out negative half the area of this circle. And so we know the area of the circle is what? It's pi r squared. So this is going to be, r here is 2, so 4 pi. So the area of the half circle is 4 pi over 2, which is 2 pi. So our integral, our definite integral, is equal to negative 2 pi. It's negative area because this function dips below the x-axis, and that's the area that we want. All right, so let's stop this video here, and then we'll keep going with some properties of these integrals.